Okay, hey guys, this is review, I guess, for the upcoming quiz 2. Sorry this is posted so late. It actually takes a surprisingly long amount of time to come up with problems, because oftentimes the problems, even simple problems, turn out to become quite complicated. And I realized after the first quiz that complicated problems are not necessarily what the professor has in mind. So anyways, I'm just going to give you guys some basic problems, and we'll go over some brief concepts that I think are important and that might have gotten overlooked a little bit. Quiz 1 focused a lot on conceptual questions, or not focused a lot, but it had like what, a third or half of the exam was conceptual questions, and I don't really know what kind of conceptual questions you would have on this exam, mostly because we haven't had that many conceptual questions in the homework. So, but yeah, let's see. Okay, so I'm going to do one basic truss problem and we're just showing you how to find deflections in there. This is the problem we'll be doing. I'll work everything out so you don't have to copy this down right now. And then this problem is it's half of your pre-lab, and I'll just calculate the deflection and rotation at C using a variety of different methods, or not a variety. I'll use differential equation method and moment area methods, just so you guys get a feel for how those work. And I was going to go into this problem, but I was looking at it and there's a little bit too much going on for us to go into that one in a reasonable period of time, and it ends up becoming like a very long problem. So I don't think you guys will want to go through this. And something like that should not be on the exam, based on what the professor did for exam 1. Okay, so let's look at the first case. Actually, before we even go into this, let's cover some basic things really quick. What are forces? What are examples of forces? So forces has units of force. This is Newton, pound. You'll notice that pound we often think of as being unit of weight, but weight is just a force, right? So forces are weight. They're usually point loads or distributed loads. And like you could have concentrated mass or concentrated weight or distributed weight. Yes. I think, what else do we have? What is moment? Moment is force times distance. And this is usually concentrated. I don't think you can have distributed moment. It wouldn't make too much sense. At least in my mind. Like you can write a math problem with distributed moment, but physically I don't think distributed moments occur very often. They're just force times distance. So this is Newton meter or pound foot. You also have work, which is also force times distance. This is perpendicular distance. This is parallel distance. So if you can imagine, I have this is Newton times meter, or pound foot, or joules. And what do I mean by perpendicular distance? This is the distance the force travels. This is the distance, this is like how much this is the distance separating something. So if I have it like this, this is FD, this is the perpendicular distance. And if I have some block, I push on F and it travels some distance D, that is parallel distance. It'll make more sense in context, like it'll ask for work and you'll know that to use distance. What else is there? What is E? E is usually given, E is modulus of elasticity. It usually has units of pascals, which is Newton per meter squared. Note that this is equivalent to kilonewtons. Sorry, no, let me step back. Normally, for most materials that we work with, we're going to be working with gigapascals. And that happens to be equal to 10 to the 9th Newton per meter squared. But you can get rid of this 10 to the 9th because it happens to be equal to a kilonewton per millimeter squared. And this is actually the unit that you will be using. You normally don't express gigapascals in newtons per meter squared times 10 to the 9th. Usually expressed in terms of kilonewtons per millimeter squared, because millimeters, your area is usually measured in millimeters. Your moment of inertia is usually measured in millimeters, so this ends up becoming a handy unit. And also your load tends to be in kilonewtons, so that ends up working out well. What else is there? Your moment of inertia is in units of length to the 4th. So this is meters to the 4th, millimeters to the 4th, inches to the 4th. And area is length squared. So those are all things you should keep in mind at some point. You have a table. This will be given to you. It is currently available online. It has properties of areas, integrals, whatever you guys could want. You'll notice that this table here is in terms, it already has, I'll bring this up closer, you guys can just see this I guess, but it looks blurry on my screen right now. I don't know if it clears up for you guys, but this is in the integral. It already has the integration. So just choose the shape of your Q diagram, choose the shape of your P diagram, and the product of those two things is somewhere in here. So this can save you a lot of time if you know how to use it. Okay, what else we're going to talk about? Let's just go into the problems, I guess. I'm not going to split this video up. I'm going to just leave it in terms of how long it is. I'll just upload a single video rather than uploading it as a playlist of videos that I usually do. The downside of that is that if I make a mistake, that I'm not going to recreate the whole video like I usually try to do. But that should be fine. Okay, so let's work with a truss problem. We've done a few of them, but I think a simple problem like you might have on the exam would be a three-legged truss, which is LL and square root 2L. Let's call this A, B, C. We'll have a roller here and a pin here. Just for fun, let's give these things, this is a truss, so we only have axial forces, so we only have to worry about axial deformations. Let's say this has properties AE, AE, and this long member has 2AE. And yes, so the first thing is always make your table, and I'm going to make my table on a separate page just so that I can flip back and forth easily. Your table is going to have, it's going to be very short. Notice how we only have 3 members or 3 rows. We will only have 3 rows, sorry, because we only have 3 members. This is AE. Normally you split these up into separate columns, but because our A and E are the same, we just multiply it by 2 AE or 1 AE. I'm going to put them in their own column. We have length. We have the P system. And then we'll have several columns for the Q system. I notice how I have 3 degrees of freedom. This point can move in the X direction or it can move in the Y direction. This point can only move in the X direction because the roller prevents Y translation in the Y direction, and the pin here prevents translation in both directions. So I only have 3 possible points that can move. So let's find the deflection of all 3. Sorry, I forgot to put my load on here. My load is going to be here. Some load P. And I want to find the, let's find delta A in the X direction, delta A in the Y direction, and delta B in the X direction. So now we come back to our table and I say, well, if I need 1 column for each of these deflections. So I'm going to call this FQ AX, FQ AY, and FQ BX. Okay. Now let's start calculating the forces. For now, okay, so right away I can see that my CY, otherwise the table would bleed through the page. My CY, sorry, CX is just going to be P. It's going to be negative P. I'm assuming my X direction is X and Y. It's going to be negative P. My moment about B, my CY force is going to be P, and my BY force is going to be negative P. Now let's just find the forces in the P system. I'm just going to use method of joints because we want to find the force in every member. So can you guys tell without even looking at this that this is going to be a 0 force member? And the reason why that is there's nothing here that can support a axial force in a horizontal direction. For example, let me draw out point B. Point B, this is BC, BA, and this is BY. If I do sum of forces in the X, BX is equal to 0. Sorry, BC equals 0. My forces in the Y, BA plus BY equals 0. BA equals negative BY equals negative P equals P. So the way I have my sign convention defined, tension is positive. So this is P in tension equals P in tension. Now let's look at joint A. At joint A, I have a force P going this way. I have a force BA going this way. And I have a force AC going this way. And if I do sum of forces in the X, then I have AC times cosine, let's call this theta, plus P equals 0. If I do all that, then I'll just get AC, cosine theta becomes AC 1 over square root of 2 plus P equals 0. And for AC equals negative P. And note that I normally don't want to leave this in terms of a negative sign. I'm going to just say AC equals square root of 2P compression. So let me double underline whatever I've calculated so far. And we already have that the last member, BC, is 0. So let's go back to our table. I have 3 members. Let me label these rows really quick. I have row AB, AC, and BC. My AE for AB, which is defined in green here. Let me use green. Let me see if I can fit both of them on the same page. AB, so AC is the 2AE, so this is AE, 2AE, and AE. Right, because I said that I defined AC to be 2AE. My relative lengths of these, this is L, root 2L, and L. And my FP my FPs are just the forces that I already found, so let me plug those in. I found AB to be P. I found AC to be negative square root of 2P. And I found BC to be 0, right? 0. I said that I wanted to get rid of the signs, but that was just for notation purposes here. The only thing that matters to me is whether it's in tension or compression. Over here I need to include the signs because I'm going to be using this as multiplication later on, so I won't be able to I can't just use words in math. You can use letters in math, that's fine. You just can't use words. Okay, now let's look at FQAX. To find FQAX, I just want to apply a virtual force in the x direction, but let's see if you guys notice this. I'm applying a unit. This is my FQAX system. I applied a unit force at the x direction at A. Do you guys agree that this diagram is exactly the same as this diagram? I'm going to get the exact same values in this column as I did in this column, except my P will be 1, right? Like if I replace this with P, I would get exactly the same values. So I go the other way. If I replace this P with 1, if I plug P equals 1 into all these equations, then I will get this column. That just happens to work out in our case. So let's see what happens. We get 1, negative square root of 2, and 0. Let me make sure that I have the values correct. Yes. Okay, so that was easy. Now, next system, let's look at FQAY. FQAY, I'm going to apply a unit load going upwards. And do you see right away what my zero force members are going to be? Okay, so let's find the reactions first. Sum of forces in the x direction. I have this is B and C. Cx equals 0 because there's no forces in the x direction. What about Cy? If I take moment about C, I end up getting that By is equal to -1. And therefore, by sum of forces in the y direction, my Cy equals 0. Right, because if I have 1, and this is going to be -1, and this is going to be 0. If I take sum of forces 1 minus 1 is going to be 0. There's nothing. Cy is going to be Cy plus 1 minus 1 equals 0. Therefore, Cy equals 0. So right away, I can say that this is going to be a zero force member, and this is going to be a zero force member. So I can just plug this back into my chart, because the only force that I have that is relevant is at B. BA, BY, sorry, this is 1. So BA equals 1. So it's 1. Notice that it's in tension, right? I'm pulling this one upwards, this one can't move. If I'm pulling on something that is not able to move, then I'm causing tension in it. And my other two things are going to be 0. Last one is FQBX, and likewise that is also going to have several 0 terms. Let me look at it this way. I can apply unit load in the horizontal direction here. 1 is going to be 0. It's going to be perpendicular. This is going to be a zero force member for the same reasons that we had before. And likewise, this will be a zero force member also. And I'll let you figure this one out for yourselves. I'll give you guys the final result. BC will be 0. Sorry, BC will be 1. Everything else will be 0. Zero, 0, 1. So now I have this table, and in order to use this table, remember what my equation is. My equation is, before I drop the thing that's holding up my camera, I should take a picture and show it to you guys one day. It's actually I have a pitcher of water holding up a tripod, which is holding up my water, or holding up my camera in order to give me enough clearance. It works. It's an engineer solution, right? Anyway, your equation is FQ, FP, it's technically Q times over AE. This is just to get your units correctly. Notice that you have 2 force terms in here. The product of two force terms is going to be Newton squared. I have a Newton term here, so my Newton will cancel out of Newton, and I'll just be left with this whole thing will end up having units of force. I forgot my L here. So if I don't have enough space in these columns here, but if I'm just going to number these columns. Let's call this column 1, 2, 3, 4, 5, and 6. Then this is going to be this, was it FP, FQ, AX, L over AE, is going to be columns 3 times, or column 3 times column 4 times column 2 divided by column 1. So it's going to be 2 times 3 times 4 divided by 1. in each of these rows. So I didn't actually calculate that out myself, but this should be relatively easy because we have nice numbers. So Fp times Fq is going to be P times L, just L. This is PL over AE. The next row is going to be it's going to be square root of 2 times square root of 2 gives you 2 plus this p term, so it's going to be 2p. The negatives will cancel out. I have a square root of 2p here, so it's going to be square root of 2pl over 2ae. So this ends up, the 2's will cancel out. I'll just be left with the square root of 2 pl over ae. Then down here, notice that I have 0 times 0, so this is just going to be 0. If I want to find now delta ax, I just need to add up these terms. PL over AE. I'm just going to, this is for simplicity. This is 1 plus square root of 2. I remember, notice because like I have the same, I can just factor out PL over AE here when I'm adding these together. And I can do the same thing to find the next two displacements. Okay, I'm hoping that this problem is actually useful for you guys, because just based on what happened in the midterm, like he ended up giving you guys pretty simple problems, and I think that's his goal. The homeworks are a lot harder than the exams, I think at least, and I think that's good for you. The classes I've learned the most in, at least, are classes where we had ridiculously hard homework. Example, you guys can try taking and solve Schrodinger equations, time-dependent Schrodinger equations. Yes, those are no fun at all. Those are an enormous amount of work, but you end up learning a surprising amount. And the exam just tests how well you've actually learned, rather than how well you can do tricky math. Okay, the next problem, the last problem I'm going to do, is your deflection problem. The reason why I was trying to do a frame originally was because I thought that the frame I was originally going to do was this one, but there's too many small details in this frame for me to be comfortable with the solution that I have, and so I'm not going to go into that one with you. But if you'd like, you can try practicing with this one. I see this problem as being like a good example of like it's fairly simple loading case. It has some interesting properties because you have no moment in this arm, you have parabolic moment in this arm, and you have some axial forces. You have axial forces in this arm, so it tests a little bit of everything, but and you can just choose whatever you want to find and try solving for it. I don't trust my solutions for this one, so I won't be able to show you guys what I did. But if you want to try working on this, and then maybe stopping by one of our office or my office and seeing me, we can maybe work out something out there. The problem I am going to do, however, is the one that, if I can find it, is the one that we did, or that you guys did / will do for the pre-lab. And that is this problem. And I really like this problem because it's very easy to use any method you like. I can show you how the methods work without easily, without worrying about getting the wrong answer. And yeah, it's a very interesting problem, particularly from the differential equation point of view. Just stop saying but let's get started. The problem is just going to be, here's a cantilever load case.